In this video, we are going to go through more examples of how to calculate the reactionary forces. So in this example, we have two applied point concentrated loads. We have an 8 kip load applied 5 feet from support A, and we have an 11 kip load applied 9 feet from support A or 11 feet from support B. So my question to you will be, okay, what are the reactionary forces of the support connection at A, and what's the reactionary force at point B? Let's go over to Excel for this, and don't make fun of me. This is not going to be easy using a mouse to draw this out. But we can write out our fundamental principles of equilibrium, and that's that the sum of all forces in the y direction must be equal to 0. The sum of all forces in the x direction must be equal to 0, and the sum of all moments at any point must be equal to 0. And you can look at this and say, okay, do we have any forces in the y direction? Yes. So we're going to put a little check there. That's supposed to be a check mark. Do we have any forces in the x direction? No. So we're not going to be able to have anything over here. We can actually cancel that out. And then, will there be moments applied? Yes. And that's going to be a pretty typical setup where we realize we don't have any horizontal forces, so we can ignore the middle one. So the sum of all forces in the y equals 0. Remember, we call anything going up positive and anything going down negative. So we're going to say that F of the reactionary force of A minus 8 minus 11 plus F of B equals 0. And that would be how we set it up. And I think you can quickly tell that, well, I think it might be easier to move the 8 and the 11 over to the other side. So I'm going to write the reactionary force of A plus the reactionary force of B is equal to 8 plus 11. And right here, I think that you guys should be able to get to a point where instead of writing out this part, you go directly to this step. And this step is just saying that, well, put your equal sign first. And then anything in one direction, put on one side of the equal sign. And then anything in the other direction, make positive on the other side. So this and this on one side, these two on the other. And you can directly go to there. Okay, now this is one equation, but I can't go any further. So we're going to leave that alone for now. Let's just write out the next step, which would be f of a plus f of b equals 19. And then we'll stop for that one right there. And now we have one equation with two unknowns. Now we're going to look at the sum of all moments about a single point. And you can choose any point you want to analyze. You can choose point A. You can choose point B, you can choose right here, you can choose right here. I can even choose right here. If you happen to know what that was, you can make up an arbitrary point. We can call that 8 feet away. Now, you wouldn't want to choose that one because it would make more work for you. So the rule of thumb is to choose a point that cancels out one of the reactionary forces. So if I analyze point A or point B, one of these will have a distance of 0, which would then cancel out. If I do right here, or anywhere in between, these would both be variables, and then we would have an equation, a system of equations with two equations and two unknowns. Yes, you know how to solve that, but why even give yourself more work? We might as well just analyze point A or point B. So pick one. I'll do point A for no real reason. Point B would have been just the same steps. So we're going to look at the sum of all moments about point A is equal to 0. Again, put everything in one direction on one side and then everything on the other side. So if I'm analyzing point A, I hope you realize that, if we have our moment equals our force times our distance, that's a multiplication, looks like a subtraction. Our distance from this force to point A is 0, right? Force A is applied directly at point A, so there's no distance. So if there's no distance, distance equals 0, force times 0 is 0. So I'm not even going to analyze this force anymore because it goes away. So now we have 8 kips times distance of 5 plus 11 kips times a distance of, not 11, we're going from point A. So the distance to point A would be 9. And this is going to be equal to, and now we have it going in the other direction, which would be the force of B multiplied by the distance, which is 20. And now we have a simple algebra expression. We have 8 times 5 plus 11 times 9 equals the variable times 20. We can solve that. If I was smart, which I'm not, I would have had a calculator ready to go. So let's just do that now. We have 8 times 5 plus 11 times 9 equals 139. And we're going to divide that all by 20. Gives me f of b equals, what was that? 6.95 kips. Okay, cool. Now that I know this, I can now plug this into here. And again, that's an awful plus sign. Don't look, don't look. Yeah, that's a fine, good plus sign now. Okay, so now that I know that f of b is 6.95, I could pretty easily find what f of a is. So f of a would be equal to, let's clear that out, 19 minus 6.95, which would give you 12.05. So f of a is equal to, I have an awful short-term memory, 12.05 kips. Okay, we just solved the problem. And now let's analyze this for a second. We know we have 8 kips and 11 kips pushing down, which would be 19 total kips. So if I add these two together, I'll get 19 kips. Also, you can see that this is loaded closer to A than B, so it also makes logical sense that f of A would be larger than f of B. It's kind of a way to help you self-check yourself. And that's example 1. So let's look at another example. And I think I want you guys to try this one on your own. I will give you the answer for it, but I want to see if you guys can get this. So I suggest pausing the video at this time and then checking your answer, which I'll post on the next slide. So pause it now and try this yourself. So I'm assuming you tried it yourself, and here are the results that I got from this. The reactionary force at A is 17.46, and the reactionary force at B, that should say B, let me fix that right now, should be 14.54. And if you add them up, it should be equal to these added up, and looking at it, f of A should be a little bit larger than f of B, since most of the weight is closer to that support right there. So now we're going to move on to distributed loads. So what if we have a uniform load? We have our uniform load, which we will call W, is equal to 120 pounds per linear foot. So for every linear foot we have going down, we have 120 feet being applied. And this is going on for 24 feet. So these are actually not difficult at all. It's the same process. We just have to do one extra step. And that step is we are going to rewrite the uniform load as a single point load right in the middle. Okay, hear me out. We have 120 pounds per linear foot going on for 24 feet, which means that total, this load being applied is equal to 2,880 pounds. Instead of putting it as a distributed uniform load, we're going to call it a single point load right in the middle. And we're not saying in the middle because it's the middle of the beam. We're saying it's the middle because it's the middle of the distributed load. For example, if this distributed load only went from here to here, we would say it's equivalent to being applied right in the middle of it. So now that we have this rewritten as a single point load in the middle of the uniform load, you guys should know how to solve it. And in this instance, it's applied right in the middle, so you can solve it even easier. I can just say, okay, it's half and half. So that's it for that one. And now we might be able to apply both of those principles. Now I have a uniform distributed load of 650 pounds per foot and a point load of 4,000 pounds 6 feet away. So what would step one be? Good. It's to rewrite this distributed load as a single point load right in the middle. So I have 650 pounds per foot times my total distance of this, which is 20 feet. And we're going to apply that right in the middle. So let's just, I guess, follow the PowerPoint. So we're going to sketch a free body diagram. And now we have our reactionary forces. We know that there are no horizontal forces, so we're going to ignore that. And now let's do our sum of forces in the y direction is equal to 0. So we have our reactionary force of A plus our reactionary force of B minus our 4,000 minus our distributed load rewritten as a point load, which is 650 pounds per foot times the total feet. And we know that the total force coming down is 17,000 pounds. So the sum of our reactionary forces up meant to resist that must be the same. We have to stop here and move on to our moments. And again, that's just saying that the distributed load right here is equivalent to a concentrated load in the middle. Choose a point, analyze either point A or point B, does not matter. They did some moments around point A, fine. So we have our one force of 4,000 right here, which is applied 6 feet away. So we're going to do 4,000 times 6. And then we have this load right here, which is 13,000, and it's halfway, which is going to be 10 feet. And then that is all going to be equal to this one, which is being pushed in the opposite direction at 20 feet away. So we have our 20 feet times our force minus the rest. And you can move those over to the other side. And again, I think you should be able to get to a point where you have your reactionary forces on one side and then your applied loads on the other side of the equal sign. And you can do this all at once. Read through this, make sure you follow the steps, and you should find the reactionary force at point B to be 7,700 pounds. Once you have that, you can apply that into this variable right here, and f of A could be solved pretty simply from there. And just to give you a little bit of a math connection, we just solved a system of two equations, two unknowns. You guys have done this since probably Algebra 1. Okay, that will be it for this lesson. Of course, please email me. I can give out my Google Voice number. We can arrange a time to talk on the phone. We could FaceTime. Like, guys, we're trying to be flexible. I mean, this is an unusual predicament. We gotta drastic times call for drastic measures, right? We're gonna have to think of different ways to communicate and still be a class.